bring something. I was coming today, here it is, we'll just come back down like this. But I have some stuff that lies under my deck that runs the water away from the house. It looks just like this. And I bought it at Home Depot, it was real cheap. But it's amazing, now it doesn't flood behind my house. I just gave it a slight slope, you know, directed away from the house. Water comes piling in here, gets on this thing, underneath the deck, and just what? Runs along this stuff right outside, you know, right back down to the, away from the house. But that, which one, to let you know, there's actual math equations that can represent, that's a cylinder. Let's do quadratic surfaces. Quadratic surfaces, now. How many variables will we in quadratic surfaces? 3. So we already know about a plane. What's a plane? Like 2x plus 3y plus 5z equals 8 or something, right? But the key about quadratic surfaces, how many variables?
3.
3 variables. All right. Well, let's start out with the utmost, most important one. You'll see it often. What if you got all of them summed together, they all got squares, and then it just equals a number like, I don't know, 4 or something. Do you remember that from our first class? That's a sphere. Y'all recognize it? Where's it centered?
2.
It's a sphere, centered at the origin. What's the radius?
2.
2. So if you want to make a picture, feel free to just stick a little ball right here. Radius equals what? Quadratic surface. X squared, y squared, all, see it's got 3 variables. Not a cylinder. It's a quadratic surfaces. Cylinders are surfaces too, but we just call them cylinders. These are quadratic surfaces. It's one type. Okay. But they'll have 3 variables in them. Alright, let's just talk about this then. 4x squared plus y squared plus z squared equals 4. Alright, that's close to that. What's that stupid 4 doing to it? It's not a perfect sphere anymore. It's stretching it. Alright, let's think of some words. I'll give you the proper textbook word. It's on that sheet. What? I think it's like a football, right? Okay, it's like I took some kind of what? Sphere and just smushed it. Like a football? What? Like a blimp? Like a blimp? And you go, well, what's the proper word? What do they call it? An ellipsoid. It's called an ellipsoid. A football, blimp. If you want to put other words down. The football, blimp, ellipsoid. I want to know which way it's more stretched though. You remember how to do this? You want to make a rough sketch? I use the intercepts. What if x and y are 0? What's z?
Plus minus 2.
Boom! What if y and z are 0? I'll hide these.
Plus minus 1.
Good. So what he's doing is just plugging it in. And one more, what if these are 0s? I just use the intercept. Plus or minus 2. If you just wanted to see which way it's more elongated. Looks like it's stretched more along the x-axis. I mean, this is on the z-axis, right? And by the way, this is when I sketch these, you might just extend the z this way, extend that a little bit more that way, and pull that more that way, where this was the y, this was the x, this was the z, so you get the pluses and minuses. Plus or minus 2, boom, boom, psh, boom, boom, psh. It's more stretched that way, but here it's just like a 1 and a negative 1, and also on the y it went out too. And you can do one trace this way. You want to trace one through these this way. And they connect it. You know, it's not a perfect sphere, but it's what? It's just an ellipsoid. But it did get stretched more along this way, right? Along the z and the y-axis. It's more scrunched in at the x-axis. All right. Now, this is very important. I'm going to put both of these at the same time, okay? Z equals x squared plus y squared. Can I erase that ellipsoid? Z squared equals x squared plus y squared. Okay, this is huge. Don't they look the same? Don't they look the same? They do. These two look the same. Can you imagine throughout our course, how many times we're going to see that? How many times we see that? All the time. Now I want you to be able to look at it and go, gosh, I didn't memorize these. I think it's memorization. I think it's more conceptual. These are quadratic surfaces, but they both look the same, don't they? Except this is missing the what? Square. So I think if you just fall back on your old algebra concepts, you'll know exactly what these two things look like. You know the quadratic surfaces, right?
Mm-hmm.
So I'm going to hide that. I'm going to start here. Hide that. What does that look like? What kind of equation? To me, it looks like a parabola. Do you agree? Two-dimensional space, like z equals x squared, would be a parabola from on the z and the xz plane, right? So what this becomes is, because that would just be what? Like a parabola? This is called a paraboloid. Alright. But then let's see how I did this, not by memorization, I just what? I hid this. I knew it wasn't a cylinder. But I said, oh, this is like a parabola, like y equals x squared, parabola, paraboloid. A paraboloid is like a windsock. This letter here is going to be the center, bless you. This will be the center of the paraboloid. So it's a windsock. So this, the variable that's isolated by itself outside the equal sign will be the center there. So when I'm going to sketch a nice paraboloid, what is it? It's like a windsock that just keeps opening up like this. So I'm just going to, and it's circular. Come up like this. I'll come up like this, but I'm just going to draw at least just one circle, one trace. I think one trace is good enough. And there's my parabolic cylinder. All these, like cross sections, would be circular. So it's really what kind of paraboloid? This was a circular paraboloid. Alright? Hey, what would make it an elliptic paraboloid? Elliptic, if it had like a 4 here and a 1 there, or a 9 there and a 1 there, then it would be more what? Like an elliptic paraboloid. Hey, what would this look like then, before I do this one? Z equal to 8 minus x squared minus y squared. What would that look like? You recognize it? You go, what is that? Oh, it's got all three variables. It's got the x squared and y squared but z, so what did the minuses do? Took this thing, inverted it, but it shifted up what? 8 notches on the y-axis, and then it started fanning out like that. Does that make sense? Man, you're good. That's exactly what would happen. I mean, just a rough sketch of like, what's going on? It doesn't have to be perfect. 1, 2, 3, 4, 5, 6, 7, 8. And just let this thing kind of fan out like this, and you're like, that's what's happening. And we see things like this all the time. Okay, how about this? Let me hide this. It's look just like it, and I'm going to think about that in two-dimensional space. Z squared equals x squared? Well, isn't that like if I square root both sides, what would I get? Z equals x. And I'll put a plus minus in front because I took the what? Square root of both sides. Do you know what that would look like in two-dimensional space? If I square root both sides, I get this. Which means I got a line that goes like that, and I got a line that goes like that. You all agree? Once again, I don't do this by memorization, it's conceptual. I'm like, well, that's the relationship there. But now you go three-dimensional. You know what happens? In the circles form, guess what this turns into? What does this turn into? A cone. And you can call it a double cone. If you want to call it a double cone, because there's going to be two of them, right? So this will be a double cone, but we'll just write cone. It's a double cone. How do you know which axis it's centered on? The variable that's isolated outside the equal sign. That's how you know where it's centered. Right? So this would look like what? Circular cone, right? Because we can have elliptical cones. It's a double cone. Cool. Hey, later on in this course, you may see something like this, where the writer takes the square root of both sides. If I took the square root of both sides, I get what? And what would be in front? A plus or what? Minus. This is the top cone. And what would be the bottom cone? Just what? So most of the time you might only see this later in the course. But I want to let you know it just came from doing what? Square root of both sides. Hey, does anyone recognize the difference between a paraboloid and a cone? Cool. Hey, a couple more. Yeah, just a couple more. A quadratic surfaces. What have we seen so far? The almighty ellipsoid, cone, and paraboloids, right? Well, now we have something called an ellipsoid. Got all three variables. Oh, we did the ellipsoid. This is called a hyperboloid. Yeah. And I'll do it again. Both of these are hyperboloids. That's a hyperboloid. That's a hyperboloid. These kind of look like the spheres before, don't they? But what's new? First they have all three variables, right? What was different about these than with the cone? The cone was just x squared equal z squared plus y squared. There was no number in there. I see a number's involved now, right? But it still has all three what? Variables. But what's new about this, different from the sphere, is this has a what? A minus. So when you see a minus, Bob, you know this is what we call a hyperboloid. If it has one minus, it's a hyperboloid of one sheet. Okay. How many minuses did this have? Subtraction signs. So you know what they call this? They call this a hyperboloid of two sheets. All right. Well,
Are these sheets the plane? Does the plane?
and we need other words to think about this. What I mean is something in real life. And I'm just going to hold this up. You're close enough. There's my pickup on there. What does that look like? It's like a nuclear power plant. Oh, that's what hyperboloids of one sheets look like. Hyperboloids of one sheets look like, perhaps a nuclear power plant. All right, that's what they look like. Now, which axis will be centered on? Where the minus is in front. So, and see how this is the coefficient to what? The letter z. So I'm going to draw something that looks like a nuclear power plant that's centered on which axis?
Z.
Z-axis. Look, circular here. It would bend in, but then bend back down. It's an open surface, so this would continue infinitely, right?
Mm-hmm.
In fact, of all the surfaces I've been doing, the only one that's a closed surface is the sphere or the ellipsoid. Everything else just kept what? Opening. And we're only talking about the surface. The cones did it, the paraboloids did it. This would do it. The only thing, in terms of the word closed surface, you'd say the only thing closed up was the sphere or the ellipsoid. This would continue. By the way, you want to know what the radius would be right here in the plane? This is where the x-axis, the xy plane. Remember, for the xy plane, what would z equal? If you were just curious, what's the radius right there? You can see there's like an intersection right there in that little circle. If you said z equals 0, what equation do you get? X squared plus y squared equals what?
1.
1. What's the radius of that little circle?
Half.
It's a radius of 1, isn't it?
No, that's the diameter. R square, right?
Yeah, but what we're saying is,
sorry,
to like if we said, hey, in the xy plane, z must equal 0.
Yeah.
So we're like, okay, hide that. Looks like you got the equation x squared plus y squared equals 1 right there.
Yeah.
It'd be a nice circle that radius 1. But then the radius just keeps what?
Right.
Getting bigger and bigger and bigger. Cool. Now let's come over here. This looks like, when it's hyperboloids at two sheets, it's like you get two, almost like satellite dishes. Now, which axis is it centered on, though?
Z.
Over here, it was centered on where the minus was. In this scenario, it's centered where the two minuses aren't. It's where the positive is. Where's the
so
positive?
X.
See it right there? So I'm going to draw two just satellite dishes. I'll come 1 unit off the origin right there. Just go like that. And then everyone, would you extend this x-axis and go negative? Because there's another one. And put it right here. Just bend it off like that. And just put a circle. But these are, once again, open surfaces. They would just keep what? Opening up. Cool. Can you see there's a satellite dish? There's a satellite dish there, everyone? Cool. There's two. All right, there you go. Okay, again, how do you know which axis they're on? The what?
The one that is
The one that's positive. How do you know this was centered?
the one that is negative.
The one that was negative. Cool. Hey, there's one more surface, I never have you sketch it if you're curious, but it's called the hyperbolic property. All right, looks like a saddle. So I just want to put the equation right here. You don't have to sketch it, but it's called the hyperbolic paraboloid. All right, and what did the circular paraboloid look like? Z equals x squared plus y squared. What's the difference? See, it's not a cylinder. It's got all three variables, but what's between these? A minus. You don't have to sketch that ever by freehand, at least for me. But you can see what the image looks like in the book. And you go, what does it look like? Looks like a saddle. Like the saddle and actually on the back of like a horse or something. That's just saddles, okay? You know, we'll talk about like later in this course saddle points. And right before you pack up, can I just blast like 5 or 6 images on the board and you just tell me what they'd all look like? Cool. We'll wrap up. Only take a second. I'll just write a bunch. Here they come. Well, how about? Let's see. Take that one. Oops. I need a different barrel. Okay, there's 2 of them. I need a few more. How about x squared minus y squared plus z squared equals 1? How about x squared equals y squared plus z squared? How about 9x squared plus y squared plus z squared equals 9? I'll throw this guy in a mix. Okay. Hey, we'll wrap up fast with this. You know, we can talk about it, and I can make a little sloppy sketch. We'll bolt out of here. Sound cool? All right. What do you think? Sphere. What's the radius? 3. Center where? Origin. So that's a sphere. That was easy. Come way down here. What do you think?